Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The landscape of modern mathematics is rich with profound theorems, elegant proofs, and intricate structures that reveal connections between seemingly disparate fields. Among these achievements, Grigori Margulis' 1981 monograph, Discrete Subgroups of Semisimple Lie Groups, stands as a monumental contribution, reshaping our understanding of these fundamental objects. This essay undertakes a detailed examination of Margulis' work, focusing specifically on a critical evaluation of the claims, arguments, and results presented within each section, offering insight into the impact and enduring significance of his contributions. Section 1: Introduction to Lattices in Semisimple Lie Groups. The initial section of Margulis' monograph lays the groundwork for the entire edifice, defining the central objects of study: discrete subgroups, lattices, and semisimple Lie groups. The author initiates by establishing the fundamental properties of Lie groups, emphasizing the significance of semisimplicity and the associated algebraic structure. The core claim here revolves around the assertion that understanding these groups is pivotal to resolving numerous problems in geometry, number theory, and representation theory. Margulis meticulously describes the notion of a lattice, a discrete subgroup of finite covolume, highlighting its crucial role as a bridge between continuous Lie groups and discrete algebraic structures. He emphasizes the importance of studying quotients of symmetric spaces by the action of lattices, spaces often referred to as locally symmetric spaces. The claim is that the geometric and topological properties of these quotients reflect the underlying algebraic structure of the Lie group and the arithmetic nature of the lattice. Evidence supporting this claim is woven into the narrative through illustrative examples and references to classical results. The section argues that the density of the lattice is not merely a quantitative measurement, but a reflection of the group's global structure. A major point is the distinction between cocompact and non-cocompact lattices, where the former gives rise to closed manifolds of finite volume, and the latter to non-compact spaces. The introduction underscores the importance of lattices in understanding the geometry of locally symmetric spaces. Implicit in this introduction is also a suggestion that further analysis will reveal significant rigidity phenomena in these spaces. This section also points the reader to the relevance of the Borel density theorem. Section 2: Arithmeticity and the structure of lattices. This section grapples with the concept of arithmeticity, a central theme in the study of lattices. Margulis presents diverse equivalent formulations of arithmeticity, defining it as a property that connects lattices to algebraic groups defined over number fields. One claim is that a substantial proportion of lattices in semisimple Lie groups, particularly those of higher rank, are arithmetic. In other words, they arise naturally from algebraic groups defined over the rational numbers, or more generally, over number fields. Margulis provides a detailed account of the construction of arithmetic lattices, describing how to obtain them through restriction of scalars. This construction reveals that lattices are not simply discrete subgroups, but are intimately connected to the arithmetic properties of algebraic numbers. He then proceeds to argue that this arithmeticity has profound implications for the structure and representation theory of these lattices. Margulis' meticulous exposition includes the discussion of irreducible lattices. In this case, the question becomes whether non-arithmetic irreducible lattices exist, or if all such objects are arithmetic. The section foreshadows the deeper results which prove arithmeticity for groups of higher rank. Another point is that this section highlights the subtle interactions between analysis, algebra, and number theory which characterize the field. This section also prepares the ground for Margulis' profound rigidity theorem. It lays the groundwork for establishing the connection between abstract group isomorphisms and geometric isometries. Section 3: Superrigidity and Moster rigidity. Margulis' superrigidity theorem, a cornerstone of the book and his most celebrated result, is presented here. This section delves into the technical details of this theorem and its implications. The central claim is that homomorphisms from irreducible lattices in higher rank semisimple Lie groups into other algebraic groups extend to homomorphisms of the ambient Lie groups. Superrigidity means that representations of lattices are essentially determined by the structure of the ambient Lie group. The theorem asserts a remarkable rigidity phenomenon. The algebraic structure of the lattice dictates its representation theory. To prove superrigidity, Margulis introduces sophisticated techniques from ergodic theory, representation theory, and differential geometry. He carefully constructs invariant measures on homogeneous spaces and analyzes the behavior of group actions with respect to these measures. A crucial element of the proof involves using the measurable selection theorem to construct measurable maps that intertwine group actions. The section then explores connections between superrigidity and mosterrigidity, explaining how the former implies the latter. Mosterrigidity states that if two compact, locally symmetric spaces of negative curvature and dimension at least 3 have isomorphic fundamental groups, then they are isometric. Margulis demonstrates that superrigidity provides a powerful tool for proving such rigidity results, thereby establishing a deep link between group theory and geometry. It also points to consequences for the classification of locally symmetric spaces. The section also discusses the impact of superrigidity on the structure of lattices, showing that it severely constrains the possible representations of these groups. Section 4. Consequences of superrigidity for the structure of lattices. Building upon the foundations laid out in the previous section, this part examines the profound ramifications of superrigidity for the structure and classification of lattices in higher rank semisimple Lie groups. The central claim here is that superrigidity drastically restricts the possible lattices in higher rank groups, leading to strong arithmeticity results. Margulis shows how superrigidity implies that any lattice in a higher rank group is arithmetic. The arithmeticity theorem, a direct consequence of superrigidity, is presented as a landmark achievement, providing a complete classification of lattices in these groups. He emphasizes that this theorem not only classifies lattices, but also reveals deep connections between seemingly disparate areas of mathematics, such as number theory, algebra, and geometry. The author also explores the implications of superrigidity for the study of commensurability classes of lattices. Two lattices are said to be commensurable if they share a common subgroup of finite index. Superrigidity implies that commensurability classes of lattices in higher rank groups are relatively small, meaning that there are only finitely many lattices, up to commensurability, with a given set of algebraic invariants. The demonstration here relies on the fact that superrigidity severely restricts the possible representations of lattices, thereby constraining the possible commensurability relations between them. This section offers a powerful example of how abstract theoretical results can lead to breakthroughs in specific problems. Section 5. The congruent subgroup problem. This part deviates somewhat from the main theme of rigidity, focusing instead on the congruent subgroup problem, a classical question concerning the structure of arithmetic groups. The congruent subgroup problem asks whether every finite index subgroup of an arithmetic group contains a congruent subgroup, i.e. a subgroup defined by congruence, relations modulo some integer. Margulis presents his groundbreaking solution to this problem for lattices in higher rank semisimple Lie groups. The central claim is that for these lattices, the congruent subgroup problem has a positive solution, meaning that every finite index subgroup is indeed a congruent subgroup. This result is presented as a triumph of group theory and number theory. Solving a long-standing open problem, Margulis explains how his solution to the congruent subgroup problem is deeply intertwined with superrigidity. By using superrigidity, he is able to show that any finite index subgroup of a lattice in a higher rank group can be defined by congruence relations. The argument involves analyzing the representations of these lattices and using superrigidity to extend these representations to the ambient Lie group. This section highlights the power of superrigidity as a tool for solving problems that are seemingly unrelated to rigidity theory. He emphasizes that the positive solution to the congruence subgroup problem has profound implications for the arithmetic and algebraic structure of lattices. It implies that the finite quotients of these lattices are completely determined by their congruence quotients, revealing a deep connection between finite group theory and number theory. Section 6 Normal subgroups and simplicity. This section explores a different aspect of the structure of lattices, focusing on their normal subgroups and simplicity properties. The question addressed here is whether lattices in higher rank semisimple Lie groups are virtually simple, i.e. whether they contain a finite index subgroup that is simple. Margulis presents his famous normal subgroup theorem, which provides a partial answer to this question. The claim is that for irreducible lattices in higher rank groups, every normal subgroup is either finite or as finite index. This theorem implies that these lattices are almost simple, meaning that they do not have any non-trivial normal subgroups other than finite ones and subgroups of finite index. Margulis' proof of the normal subgroup theorem relies on sophisticated techniques from ergodic theory and representation theory. He carefully analyzes the action of the lattice on homogeneous spaces and uses ergodic theory to show that any normal subgroup must either act trivially or ergodically. The result has significant implications for the structure of lattices. It implies that these lattices are highly indecomposable and do not have any obvious quotient groups. This theorem reveals a surprising degree of rigidity in the structure of lattices, showing that they are much more tightly knit than one might expect. Section 7 Ergodic theory on homogeneous spaces. This section shifts the focus to the ergodic theory of group actions on homogeneous spaces, a subject that plays a crucial role in Margulis' proofs of superrigidity and the normal subgroup theorem. He develops the tools and techniques needed to analyze the behavior of group actions with respect to invariant measures. One fundamental claim is that understanding the ergodic properties of these actions is essential for understanding the algebraic and geometric properties of lattices. Margulis provides a detailed treatment of various ergodic theorems, such as the Birkhoff ergodic theorem and the Moore ergodicity theorem, and explains how these theorems can be applied to the study of group actions on homogeneous spaces. A central concept is that of measure rigidity, which refers to the phenomenon that invariant measures on homogeneous spaces are often highly constrained and determined by the algebraic structure of the group. Margulis emphasizes that measure rigidity provides a powerful tool for proving rigidity theorems in group theory and geometry. This section also explores the connections between ergodic theory and representation theory. He shows how the representations of a group can be used to analyze the ergodic properties of its actions on homogeneous spaces. This connection is particularly important for proving superrigidity, as it allows one to relate the representations of a lattice to the representations of the ambient Lie group. Section 8 Oppenheim Conjecture and unipotent flows. This section deviates from the main theme of rigidity, focusing instead on the Oppenheim conjecture, a problem in number theory that concerns the values of indefinite quadratic forms at integral points. The Oppenheim conjecture states that if an indefinite quadratic form in at least 3 variables is irrational, then it takes values arbitrarily close to 0 at integral points. Margulis presents his groundbreaking solution to this conjecture, using techniques from ergodic theory and homogeneous dynamics. The central claim is that the Oppenheim conjecture is true, and Margulis provides a complete proof of this result. He explains how the Oppenheim conjecture is related to the behavior of unipotent flows on homogeneous spaces. The proof involves analyzing the orbits of unipotent subgroups on quotients of semisimple Lie groups and showing that these orbits are dense. The result has significant implications for number theory, providing a complete answer to a long-standing open problem. Margulis' solution to the Oppenheim conjecture is presented as a triumph of ergodic theory and homogeneous dynamics, demonstrating the power of these techniques for solving problems in other areas of mathematics. This section reveals deep connections between number theory, ergodic theory, and the theory of Lie groups, underscoring the interconnectedness of mathematics. Section 9. Ranks of lattices. This section delves into the notion of rank for lattices in semisimple Lie groups, highlighting its significance in understanding their structure and properties. The rank of a lattice is defined in terms of the rank of the ambient Lie group and plays a crucial role in determining the rigidity properties of the lattice. Margulis explains how the rank of a lattice is related to its commensurability class and its representation theory. The central claim is that higher rank lattices exhibit much stronger rigidity properties than those of lower rank. He provides a careful analysis of the structure of lattices in different rank groups, showing that higher rank groups have a much more limited range of possible lattice structures. The author explores the connections between rank and arithmeticity, showing that higher rank lattices are often arithmetic. This connection is closely related to superrigidity. This section offers insights into the diverse behaviors of lattices in different Lie groups, underscoring the importance of rank as a key parameter. Section 10. Cocompact lattices. The text specifically examines cocompact lattices. Cocompact lattices, also known as uniform lattices, possess the property that the quotient space formed by their action on the ambient Lie group is compact. This section contrasts the behavior of cocompact lattices with that of non-cocompact lattices, highlighting the distinct geometric and topological properties of the resulting quotient spaces. The chief assertion is that cocompact lattices, due to their inherent geometric properties, frequently exhibit behaviors divergent from those observed in their non-cocompact counterparts, particularly in the context of rigidity and representation theory. Margulis systematically delineates the characteristics of cocompact lattices, emphasizing their connection to closed manifolds of finite volume. He examines the geometric and topological attributes of these manifolds, illustrating how they represent the algebraic structure of the underlying Lie group and the arithmetic nature of the lattice. Of course, there are relationships between cocompact lattices and non-cocompact lattices. The emphasis within this particular section is on the properties that cocompact lattices enjoy on their. Section 11. Non-cocompact lattices. This section contrasts with the previous one, focusing on the complement non-cocompact lattices, where the volume quotient by their action is not compact. These lattices give rise to non-compact spaces, exhibiting distinct geometric and topological features compared to cocompact lattices. Margulis explores the intricate structure theory of these non-cocompact lattices, highlighting the role of parabolic subgroups and their influence on the geometry of the quotient spaces. The key claim is that the presence of parabolic subgroups introduces a rich combinatorial structure to the quotient, affecting the representation theory and rigidity properties of the lattice. The section analyzes the way in which these parabolic subgroups determine the asymptotic behavior of geodesics and other geometric invariants on the quotient space. The discussion includes consequences for understanding the structure and geometry of the locally symmetric spaces that arise from these quotients. Thus, this section focuses on the specific attributes which delineate non-cocompact lattices. Section 12. Actions on trees. This portion of the text takes an alternative path, examining the actions of lattices on trees. It analyzes how these actions can be leveraged to derive insights into the structure and properties of lattices. The central claim relates to the connection between the existence of specific actions of lattices on trees and the satisfaction of certain algebraic or geometric conditions. Margulis meticulously describes how these actions manifest themselves and how they can be utilized to extract meaningful information about the lattice. It is demonstrated that the properties of the action on the tree can reveal information about the lattice's structure. Emphasis is placed on studying the quotient, which represents a graph whose properties are influenced by the structure of the original lattice. This section serves as a case study in applying geometric group theory ideas to the study of lattices in semisimple Lie groups. Section 13. The Selberg conjecture for higher rank groups. The Selberg conjecture posits that for congruent subgroups of arithmetic lattices, the smallest positive eigenvalue of the Laplacian operator on the associated locally symmetric space is bounded away from zero. Margulis delves into the intricacies of this conjecture, particularly in the context of lattices within higher rank groups. The claim he makes is that establishing the Selberg conjecture for these higher rank groups presents a formidable task, demanding profound insights into the representation theory of lattices. Margulis' analysis encompasses the challenges inherent in extending the classical Selberg conjecture to these more complex scenarios. This section elucidates the significance of the conjecture and its potential implications for understanding the spectral properties of locally symmetric spaces. The discussion underscores the formidable challenges involved in proving the conjecture for lattices in higher rank groups. Section 14. K-theory and lattices. This section investigates the interplay between K-theory and lattices, exploring how K-theoretic techniques can be applied to study the algebraic structure of lattices in semisimple Lie groups. K-theory, a branch of algebraic topology and algebra, provides powerful tools for analyzing the structure of rings, modules, and other algebraic objects. The key assertion is that K-theory offers a novel viewpoint for investigating the lattice's algebraic structure, potentially unveiling information inaccessible through conventional methods. Margulis meticulously explains how K-theoretic invariants can be calculated for lattices, revealing information about their algebraic properties and representation theory. This section discusses the impact of these invariants on understanding the lattice's structure. It exemplifies how innovative mathematical approaches can yield valuable insights in the study of lattice structure. Section 15. Bounded generation. Bounded generation is a structural property of groups referring to a finite set of elements that can generate any element of the group through a bounded number of operations. Margulis studies the phenomenon of bounded generation within the context of lattices in semisimple Lie groups. The presented argument is that the identification of bounded generation properties within these lattices offers a distinctive perspective on their algebraic architecture, significantly influencing their rigidity characteristics and representation theory. Margulis' painstaking exposition sheds light on the criteria for determining whether a lattice exhibits bounded generation, underscoring the implications for its broader structure. This section provides a deeper appreciation of the characteristics that define these lattices, underscoring the interconnectedness of algebraic structure, rigidity, and representation properties. Section 16. Conclusion. In conclusion, Grigori Margulis' Discrete Subgroups of Semisimple Lie groups remains a seminal work, a testament to the power of innovative mathematical thought. Its enduring significance stems not merely from its resolution of long-standing problems, but from its introduction of groundbreaking techniques and its profound impact on the field. The exploration of superrigidity, the arithmeticity theorem, the solution to the congruent subgroup problem, and the insights into the Oppenheim conjecture transformed our understanding of semisimple Lie groups, lattices, and their connections to seemingly disparate areas of mathematics. The detailed analysis presented in this essay aims to illuminate the depth and breadth of Margulis' contributions, showcasing the power of his ideas and the enduring legacy of his work. Ultimately, Margulis' work serves as a reminder that profound mathematical breakthroughs often arise from the synthesis of diverse fields and the willingness to challenge conventional wisdom, solidifying its place as a cornerstone of modern mathematics.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.